Okay, point it at me. Point it at me. All right, let's get going. Thanks for being here. This is the team presentations today. So we still have the attendance sheet. We still have the Meet with Dave sheet in case you have any missed lectures to make up or anything else. And everybody should have an evaluation form for the teams, just like the midterms. Okay. And make sure, if you haven't done so already, sign up for food for Thursday, burritos, sodas on this orange sheet or yellow sheet, so I can order the proper amount of stuff. Great. Okay. So don't evaluate your own team. You might go ahead and X out your team on there so you don't fill that out. Okay. And use a pen and use a good font. And I don't want a pen that bleeds through because I need both sides of the sheet. So I hope you can do that. Oh, yeah, sure. Okay, course evaluations. The VPTL evaluation is open. They encourage you to complete the course and instructor evaluations. And value is your opinions. I was obligated to say that. And on Thursday, when we'll come to class, and I have another form that a class-specific form to fill out. Okay. Just a few words about the final report. It should cover your entire quarter's work right from the beginning. You want to use the material you had from your midterm report, upgrade that to include the material since the midterm. You want to consider the markups I made and correct those. And they're due the week of March 19th, so next week. There's also an individual reflection, and these are for students who've worked on projects. And it's about how you felt about the course, the project, and your experience, also due the week of March 19th. But I understand that you guys are very busy with other things due and finals and stuff like that. So email me the date that you expect to submit these documents, Monday through Thursday. If you don't email me, I expect it on Monday. Okay? So I'm giving you a break. I want you to all do a good job, so I'm giving you the time to do that. Please, look it over. Have somebody else in your team proofread it, read it over, make changes. It's a big part of your grade. So people who have spent money on their projects, I hope you've kept all your receipts because they're as good as money. One team member will be reimbursed from each team. Car rental and mileage are not reimbursable. Shop passes are not reimbursable. I specifically asked the agency that gave me money for this class to reimburse PRL passes, and they declined to do so. So if it was up to me, I'd be able to reimburse you, but I can't. And I'll mail you instructions on all this. There's no deadline on this, so after everything else is done, you send me your receipts. So on Thursday, bring all your prototypes to class. We'll meet in here, fill out an evaluation form, and then we'll have the project demonstrations. Now, if it's as nice as it is right now, on Thursday, we're going to set up outside. If it's raining or wet out or windy, we'll set up in here, okay? So we have a backup. So the idea here is very informal, no posters, no handouts, just to stand around your project, and everybody will get a chance to rotate around and look at the great things that other teams did. And there'll be community members here as well. So it'll give you a chance to check out what other people have done. I'll bring burritos and stuff. Community members are welcome to attend. Also invite anybody who helped you with your project, whether that be a fellow student or the project suggester or somebody else. Have them come by. It'd be great. If we're going to be inside, there's AC available under the tables to show videos and stuff. Otherwise, outside, there's no AC. Okay? So for your project, project should be functional, but nobody is expecting something that's ready to go to market, okay? Always have contingency plans if things don't work out. A backup plan is good. If you want to, it'd be great to add your team logo or a Stanford logo or decal to it. That's to add some personalization. And like I said before, never apologize for things that you didn't get to and didn't work out as expected. Okay? Always mention future plans, because what you have now is a prototype. Everything is a prototype. Okay? So this is for community members, and there's a few here that haven't been here before. I want to thank you for attending these project presentations. These teams have been addressing challenges experienced by people in the local community who have disability or are older adults. They've been working for the past 7 weeks to go through a process of brainstorming, fabrication, testing, analysis, and iteration. These forms are meant to provide your evaluation of what they've done. Okay, it's 7 weeks. It goes very quickly. The students have other classes and things to do, so it represents a small amount of the 7 weeks. So read the front page about the criteria and how to score these. They'll be done in order, and each team will have 7 minutes to present, and that doesn't leave any time for questions. So no questions. If you have a question, come back on Thursday where you'll see the prototype and you can ask lots of questions. Okay. This is the presentation order. It's the same on your evaluation sheet. For students who are presenting, this is the presenter that you're using. This is forward, and this is the laser pointer, and those are probably the only 2 buttons you need. So this laser pointer works really well on this display. So, I think, Fred came all the way from Hawaii to visit us. Yeah. Pass this form back up to Fred. So give me a minute, and we'll the first team come on down. They're Danny's dudes, and I'll get you going here. Oh, we got the presenter, and I'm going to just put this microphone right here. You don't have to speak into it. Pick up everybody.
Well, hello and welcome everyone. We want to first thank you all for giving us the time and the opportunity to share our progress with regard to our project in the class. We are working on the Easy Easel project for Danny. First, we're going to reintroduce the team. My name is Israel.
I'm Dalmar.
I'm Griffith. Now we're going to meet Danny. So some of you may have seen Danny already. Danny usually comes to lectures and he's an active member of our community. He is seen here in this image consulting for Verily for their LiftWare accessible device which assists people with eating. Danny's goal for the class was to gain independence in his creative expression abilities in order to get to know Danny and empathize with his problems, we first had to set up a few interviews and get a chance to observe him painting. So from our observations, we observed that he needs assistance filling all of the white space with color due to his visual impairment, but also he had some difficulty reaching the extremities of the canvas because of his limited dexterity and range of motion due to his experience with cerebral palsy. From our observations and our meetings with Danny, we were able to synthesize a problem statement, which we were able to say is to improve the quality and independence of Danny as it relates to him being creative and expressing himself creatively. Very early on in our project, Danny mentioned to us that he loves his brother Stan, but he really needs to be independent. So we found this to be one of the core needs that had to be filled. From there, we went on to our ideation stage, where we first began by looking at existing products and researching their accessibility, etc. We looked at a possibility of working with Danny's already functional liftware to modify it and add an apparatus to allow him to paint on a flat surface, but we eventually discarded that idea because it was a little more complex and unfeasible. We looked at a jewelry making kit, but we found that nothing on the market was really tailored towards Danny's needs. Eventually, we also didn't go for that idea, but we learned that there was also an accessible easel already on the market. However, it was upwards of $700, which is relatively expensive. Like I mentioned before, these are the three ideas that we finally settled with and that we eventually moved on to prototyping phase. We had the accessible rotating easy easel, the accessible bead making station, bead jewelry making station, and an audio feedback object identification system. And now John Mark will take it away with prototypes.
After our midterm presentation, we examined our different prototypes that we came up with, and we decided to try to figure out which one we wanted to pursue. Also, we met with Dave to figure out what would be the most feasible choice. We found that for our first prototype, where we had Alexa identifying the paint colors for Danny, this wasn't necessarily the most efficient solution for that problem. It was kind of a roundabout way for him to find the paint. We found for our second prototype with the jewelry making station, it would be difficult to make this work reliably every time, and a limitation of this is that it only works with one bead, which kind of limits the creativity that Danny would be able to put into his projects. So we decided to go with our third idea of a rotating easel. Originally, we had the idea of having it be on maybe some sort of timer and being able to move in all four directions as well as rotate. We found that this is a little bit harder to actually implement than we wanted it to be, but we found an easier solution for this. So this is our original prototype from our midterm, and we kind of worked from there while figuring out how we wanted to build our prototype for the final. So our original sketch included different tilting angles for the easel, similar to a lawn chair device, with the Lazy Susan attached to the front to allow the front of the easel to rotate, which would allow Danny to reach all four corners and all the edges of the easel. The canvas would be held in place using a peg system similar to what we had with our midterm prototype. One thing we struggled with was finding a way to make the easel adjustable for different canvas sizes. We had several different ideas, none of which were very easy to make, very feasible, and all of which required quite a bit of dexterity to use. So eventually we ended up using this sort of peg system where Danny would be able to pick up this rectangle and put it into the circle that he needed and then fit the canvas inside. We used CAD to tinker with different designs and also to figure out the dimensions we wanted for our project before moving forward with actually building it. Some advantage to the design that we chose is that it's relatively inexpensive, made from wood and adhesives and screws. It's very convenient because the box on the bottom can be used to carry all the paint supplies that are needed in order to create a painting. It can be used by anybody. It's not limited to people with disabilities. This can be used by pretty much anybody who can sit at a table and paint. And our design holds 15 different canvas sizes, so it's pretty flexible.
So the final step was testing it out with Danny. So we watched him we observed both the mechanics of it and how he interacted with it, as well as watching him paint on it. We saw that it was actually very comfortable and looked intuitive for him to be able to turn it. And you can see here he's kind of using both hands at once. He was able to kind of fine tune exactly where he wanted to reach without having to move like his painting arm that much, because he could just rotate it. His brother Stan said, he seemed really impressed that this was the first time that Denny was able to paint independently and really just reach all parts of the canvas without having to ask for help in moving it. Also, the storage space seemed very convenient since they have a lot of supplies and now they can keep it all in one. But there's a couple things that we did notice, some pain points with the testing. So you'll see the top photo there, one of the pegs actually fell out and the canvas slid down while he was painting. So that's definitely a huge error that we need to correct for. So we're going to make the holes in the canvas, in the easel deeper so that it's more structurally sound and they can twist all the way in. Also, the corners sometimes protrude out, and if he was sitting too close to the table, would interfere with him. So we're considering either shaving those off a little bit or making it just easier to reach the canvas. And then also, you see on the bottom, we kind of had to hold the paint palette out for him because, well, we were on a circular table, so the table didn't reach out as far. But because it takes up so much space, this box, we thought of attaching it to the box or the canvas itself. And then just in general, maybe helping him somehow clean up or also the durability of it were two things that we thought should be improved. So next steps in the future, by Thursday, hopefully we'll have a handle on it so it can just be picked up like a suitcase. We just got that handle. And putting a paint palette on the side of the frame so that he can reach it on his own and reduce weight and finish surface on the wood. Thank you.
Okay. Next up is Team Empower You.
Go.
All right. Good evening, everyone. We're Team Empower You, and today we're presenting our door monitoring system that we've been working on over this past quarter. I'm Michael.
I'm Chase. I'm David.
And we built a door monitoring system for Empower You. For a brief recap, Empower You is a company started by Laura McIntosh. It's a company that designs a home monitoring system for high-risk medical patients to alert medical professionals as well as family members of potential medical emergencies. The problem that Empower You was facing was that Empower You didn't have a great system of being able to tell whether or not a user entered or exited their home, and this would thus result in a lot of false alarms. A lot of times, family members or medical professionals would be alerted in times where they didn't need to be alerted. So our solution needed to focus on tackling specific user and technical requirements. The user requirements that I'll talk about briefly are the sensors had to be hidden from plain view. Again, the idea that our user didn't want to feel like they were being watched. And a technical requirement were the two most important ones where it had to be battery powered and it had to use Z-Wave protocol. Z-Wave protocol is a low radio wave signal that is sent through home automation devices that Empower You utilizes in their current system. So a couple of existing solutions that we worked at that didn't really work for the solution we were trying to build were a door sensor, cameras, motion sensors, and hinge sensors, and all of these different sensors had their problems that we couldn't use for our solution, so we needed to think of different ways to approach the problem. So for our initial prototype, we have here our first idea, which was a doormat pressure sensor combined with a door sensor. So in this way, once the door has been opened, the door sensor would send a signal to the Empower You system saying that the door has been opened. And then once the user stepped on the mat, it would then indicate that the user has indeed exited the home. These two pieces of information would be able to then definitively say when the user actually did exit or enter the home. The second prototype idea was a touch sensing door handle on one side of the door. In this way, once the user touches the door handle, it would be sensed by the Empower You system, and then the Empower You system would detect activity inside the home, and if it didn't detect any activity inside the home for a brief period of time, then it would be able to then say that the user has indeed exited.
So after developing these two initial prototypes, we brought both of them to Laura for some feedback as well as direction to the rest of the project. So starting with the touch sensing door handle, she explained to us that she was concerned that the wired device would be in the user's line of sight at all times. Most elderly folk don't want a big white box and a bunch of wires coming out of their front door. The other concern was with the battery life of the touch sensor itself. Most touch sensors have shorter battery lives, and she wouldn't want the user to constantly switch out the battery. The last concern was that the touch sensing door handle would have to be adaptable to every single door handle, and she felt like this was an insurmountable task. Now for the pressure mat and door sensor idea, she explained that the pressure mat and door sensor would have to communicate via Z-Wave, so we would have to figure out how to do that. The mats are often seen as tripping hazards in an elder's home, so if we picked this project, we would have to minimize this risk, and also that the pressure mat would also need a longer battery life. So after taking in this feedback and weighing out the pros and cons of both, we chose the pressure mat and door sensor device because the feedback was more positive and it solved Empower You's problem more effectively. So the first step was to choose the right pressure mat. Taking Laura's feedback into account, we chose one that was as thin as possible, 1/8 of an inch thick. It could also fit under any rug or doormat if the user didn't want it to just be strewn out in front of the door like this. The dimensions also had to be large enough so that it covered the entire area in front of the door so that it would always be stepped on whether the user was entering or exiting. The operating temperature would have to be in a range so that the user could use it outside or inside, and also the trigger sensitivity would have to be high enough so that nothing but a person would set it off. We chose the ideal security in pressure mat to fit all these specifications. So the next step was trying to figure out how to get the pressure mat to communicate via Z-Wave. We couldn't find any Z-Wave pressure mats on the market, so we tried to make one for ourselves. We had the Z-Wave door sensor, and the pressure mat that we bought had an alarm module attached to it via wire that would go off every time the pressure mat was stepped on. So we cut off the alarm module, we stripped the wire, and we actually attached it to the circuit board of the Z-Wave door sensor. By doing so, we found that every time we stepped on the pressure mat, the Z-Wave door sensor would emit a Z-Wave signal signifying that the pressure mat had been stepped on. This solved our problem, and we were able to get the pressure mat to communicate via Z-Wave. On the right of the screen are the three main Z-Wave devices that we're using. We have the main controller that all these devices communicate with. We have the regular door sensor that we're putting on the door, and we have the modified Z-Wave door sensor with the yellow tape that allows the pressure mat to communicate via Z-Wave. Here we have a short video demonstration of the pressure mat working with the door sensor. Every time we stepped on the pressure mat, we saw that a light blinked on the door sensor, signifying that it was actually communicating via Z-Wave. So that light shines red every time we stepped on the pressure mat. It was working. So. The audio isn't us. Oh, that's there.
Okay. Oh, is
Internet Explorer.
All right, so the next steps in developing our pressure mat, we're developing it for outdoor use. The concern here was that the current material the pressure mat was made out of could be punctured and therefore damage the sensor once it was placed under the doormat outside of the home. So what we did was took paint canvas and then sewed a bag to fit around the pressure mat. Then the next step was doing an Empower You home visit. We're missing a picture on the left of our user John. You can see him with us on the right. He's a 90-year-old retiree living independently in Palo Alto, using the Empower You system currently. And our pressure mat can be seen under the doormat here with the wire coming out of the top left. This was placed in front of his door. And what we found was that our pressure mat could successfully communicate with his Z-Wave home system and signal if he was entering or exiting the home. So the final pros and cons of our prototype was that the pros was that it did not increase the potential tripping hazard already posed by his doormat in front of the door. It fit under the doormat easily and was out of view. It was easy to set up with a battery life of up to 3 years, and the cost of adding our sensor with the existing Z-Wave door sensor brought it up to a total cost of $50 to $60. Cons were that the wiring was not encased and could be easily damaged. It was also dependent on the home layout for where to place the door sensor, and the trigger sensitivity could have been activated by a cat or another animal stepping on the doormat. So as far as future plans, we plan to fully encase the pressure mat in more durable material, adhere the pressure mat to the bottom of the doormat so that it will stay with it at all times, and then use protective housing for the wire, and standardize an installation procedure for LoRa. Thank you.
Next, we have wheelchair workers. Look at your slides in there. Please. Okay, go.
Good evening. We are the wheelchair workers. My name is Erica Rivera. I'm a sophomore studying mechanical engineering, and Annie and Maddie are both seniors studying symbolic systems. And for our project, we're working with Abby and personalizing her wheelchair. A few things that you should know about Abby. She has mobility challenges. She uses her wheelchair and she has a service dog named Nathan. And she participates in various organizations. She's an artist and she's a formal art teacher as well.
Great, so we decided to embark on 2 different projects with Abby, and the first one is her personalization project. So whereas people's choices of clothing, accessories, and shoes allow them to express themselves every day, wheelchair users are required to wear their wheelchairs day in and day out for every occasion. And many of these wheelchair users, Abby included, would prefer the opportunity to express themselves using their wheelchair. And so that's what we set out to do with our project.
When looking into the market, we found several solutions. However, we found that most of the solutions, when it comes to personalization, catered to younger folks, as well as they weren't really the taste of our users. So we wanted to design something specifically for her.
Great, so we went about finding a solution. First, we started by brainstorming a bunch of really fun ideas that we think able to change Abby's wheelchair, and we narrowed it down first to the idea of creating a hard plastic cover that would feature some of Abby's artwork, and that would be clipped onto the side of her wheelchair. Now, we really liked this idea, but it presented a few challenges. First of all, the clips would be really hard to make, and it also might be hard for Abby to clip on this device to her wheelchair. So we would probably have to use Velcro or screws, and we didn't want to alter the wheelchair in any kind of permanent way. Yet we really liked the idea of Abby's art in some way and incorporating it, because Abby does do a lot of very beautiful art, and we really liked using that as part of the design. So we settled on using static cling decals instead.
So our final prototype involves these two 5x10 static cling decals, like Annie said, and they feature Abby's artwork. So the benefit of using static cling decals is that they can be used multiple times and they don't lose their stickiness, so they'll last a really long time. And we also wanted to print them out in sheets like this so that Abby could customize them even further and cut out different shapes, perhaps like cutting out the flowers. But when we showed them to Abby, she actually loved the full sheets themselves and put them on her wheelchair as such. So we were really thrilled with how pleased Abby was with this product, and she also expressed a ton of interest in using the website further to create her own designs and maybe use logos for organizations that she cares about. So we were really thrilled with how well this prototype turned out. The next problem that we addressed with Abby was the visibility project. So this problem is twofold. So first of all, wheelchair users need to light up the path in front of them so they can see where they're going in the dark, and they also need to be seen by others, other people, other cars for safety reasons. So we looked into some existing solutions.
Yeah, and when looking into some of the existing solutions, we found that the light attachments that were already created on the market, they didn't specifically work for the wheelchair that our user was using, so we decided to come up with our own designing, like our own light attachments as well.
Great, so again, we set off finding a solution. We brainstormed a bunch of different ideas, but the general trend, of course, was finding the right type of light and attaching it to either Abby, her wheelchair, or perhaps Nathan, her service dog. And what we decided after checking out the wheelchair a little bit more is to attach lights in some ways to the armrest, because that way they would be less prone to bumping off when the wheelchair made contact with something, and would also have the best chance of lighting her path. So our next step was to start researching lights, and our priorities here were that the lights would be bright enough and that they wouldn't be so heavy that they would be difficult to attach or likely to fall off. And we settled eventually, after looking at some bike lamps, headlamps, and flashlights, on a headlamp because it's the lightest and the brightest.
So our final prototype involved this headlamp and these rubber elastic bands. So we chose this headlamp, like Annie said, because it has a super bright LED light and a wide beam, so it illuminates her path in the most effective way. And we created our prototype using these elastic bands because they have a lot more traction than a fabric band, like in the photo. So we attached it to the armrest of her wheelchair, as you can see in the photos. And some of the benefits of this design is that it really holds on well to the armrest, and it doesn't require any additional appendages onto her wheelchair like Velcro or some permanent clip-on type device. And it's also, like Annie said, in a place that's super accessible for her hands. It's easy to put on and easy to turn on and off the light. One of the downfalls of this design is that although it is pretty secure, it is prone to slipping off if it gets bumped. So if we move forward with this project, we would consider maybe attaching more Velcro to the sides or using a different sort of clip that's easy to take off and take on, but would be a little bit more secure.
Yeah, so moving forward with this project, our next steps would be on the personalization front, working with Abby to design and making sure she has the tools herself to design on the website even additional decals so that she can keep personalizing as she wants to. And second of all, on the visibility front, finding, as Maddie said, an even more perfectly kind of fitting and feasible attachment for the lights that's also aesthetic. Thank you guys so much.
Next, Tony's terrific team.
terrific team. I'm Jake Bailey, Rachel, Tenzin, and Roger. And we are trying to solve the wheelchair camber problem. And Rachel's going to outline that a little bit more right now.
So according to the National Institute for Health, 2.2 million Americans need to use a wheelchair. And there's something that we've learned through this class so far. And that's that, just like a pair of shoes, a wheelchair needs to be customized for the user's body, lifestyle, and their environment. So a good example is to think of trying to climb a mountain wearing a pair of stirrups that are 3 sizes too small. Just wouldn't really work very well. So our project centers around Tony. Meet Tony, he's in the back there. Tony lives independently and he works, and he has an impairment which affects his mobility, and as a consequence, he uses a wheelchair to get around. But Tony has a bit of a problem, and that's that it can be hard for him to maneuver through tight spaces such as doorways. And part of the reason for this is that his wheelchair has something called camber. Camber is the angle that the rear wheels of the wheelchair touch the ground at. And we're going to talk a bit about the reasons why you might have camber and some of the benefits that it can provide. But the issue is that this angle increases the overall width of Tony's wheelchair, and that's a problem because it impacts his ability to fit through tight spaces. So our goal is to enable Tony to fit through narrow spaces by allowing him to vary the camber of his rear wheels whilst he uses his wheelchair. So let's think a bit more about what camber is and why it's helpful. So camber is the angle at which wheels hit the ground, and typically in a wheelchair it will vary from between 0 and 18 degrees on the vertical plane. So you can see the wheel with camber on the angled wheels on the left-hand side and those without on the right-hand side. Why would you do it? Well, firstly, because it enhances lateral stability. It makes it easier to maneuver over bumps. It makes it easier to turn. And it also enables, because the wheel's angled, it enables you to push outwards as well as down, which reduces shoulder strain. Now, camber is typically fixed. So in the picture that you can see there, the camber, the angle of the rear wheels, is being provided by bends in the rear wheel axle. Another way that it's provided in wheelchairs that have a single continuous axle is nuts that screw in and provide the angle. And the third way, which is how camber is provided on Tony's wheelchair, is individual plates that are screwed into the side of the wheelchair, and they hold each wheel. But there's a trade-off, and this is the challenge that Tony is facing, and that's the more angle you have on the wheels, the larger the overall width of the chair, and the more difficult it is to wheel through tight spaces.
So Tony laid out a few needs and design goals for us to achieve. First off, if we're going to adjust the camber of his wheelchair, it needs to go from 0 to 6 degrees at most to increase mobility and maneuverability. And the change needs to be either continuous or in incremental degree changes. He would like to be seated while this change is happening, and that's a huge goal for him, and he doesn't want to have to use tools to make this change. Some design goals for us is we need this to be simple and lightweight, and we cannot adjust the frame like the last picture here. We don't want to have to adjust the frame on the left to make it more horizontal. And so other solutions that we've found, there was a research group that actually didn't bring this to commercial use, but the ACAP group developed a product that could change the camber, but it actually required the user to hop out of the wheelchair, and took 90 seconds for them to adjust this. It was also $380 versus our solution, which is under 100, and you don't have to get out of the chair. Roger is now going to outline a little bit of our first prototype.
So we had 2 initial designs. The right one is to have a bar push out, and this would push the bracket out on a long pivot point. And this actually, we went with this essentially in our final design. And the design we presented last time used a curved wedge along with a handle. So when you pulled the handle up, you would tilt the bracket along based on the distance of that wedge. So our preliminary design concept was this. As you can see, we have the curved wedge. As you push it down, we can get this the 6 degrees of camber. However, this presented a few design issues. The first being the geometry of getting essentially a perfectly smooth curve to go along 6 degrees. That just made difficulties in machining, as well as the need to add a handle added additional time. And because the user had to stay seated and pull that handle up to change any of the camber, we were unsure if the user would have the strength to actually do that on both sides. So our new design concept used a motor, or in this case a linear actuator, on the right, which was mounted along with the shaft, which would push on the bottom side of the bracket along the pivot point. This would tilt the axle, which would essentially be mounted through the center, and that would tilt the wheels. So our solution, we had to make a custom bracket as seen on the left, the linear actuator over here, as well as a switch to throw into reverse in case we needed to pull it back to go back to the vertical point, and then the bolts we used to allow it to pivot.
So now we're just going to take a quick look at our manufacturing process. So we created the custom bracket using 6061 aluminum. We chose this because it was lightweight, easy to machine, and inexpensive. On the left, you can just see us trying to get the bracket close to size, and then in the middle, just squaring it off, making sure it's parallel. On the right, just drilling the holes for the axle to fit through and the bolts to fit through onto the wheel frame. For our linear actuator, we had to drill an extra hole just to make sure that there were 2 contact points that the bracket could push in and out of. And then on the right, you see the wiring for our battery pack, our switch to the linear actuator. So we have 2 quick videos of our solution. On the left, you have a rear view. I'm in the back operating the switch. You can see the actuator pushing out the bracket and increasing camber, and then retracting, and then bringing it back to vertical. And this is just a top view of the same thing. So it pushes out, you can see it push out there. So it's cambered, and now it retracts, and it's back to vertical. So just a quick cost breakdown. We used the aluminum from the product realization lab here, so we got it for free. The actuator off of Amazon was $65, so relatively inexpensive, and Home Depot for some extra bolts. So to conclude, we have a proof of concept. So we developed a solution that was relatively inexpensive. You compare it to the actual cost of wheelchairs that are $1,000, and then we were able to meet our design criteria, which was probably most important. In the future, we want to optimize the strength-to-weight ratio, so while the user is seated, there will be more friction for the wheels to overcome, so we want to make sure we have a stronger actuator for that. And then we also have to juggle the cost of that, so as we have a stronger actuator, the cost will go up. And then we want to improve the overall aesthetics, so then it's more attractive to the user and more user-friendly.
Next, we have the trolls. There you go.
Oh.
Whoa. That's the one, right? Okay, go.
Okay, hi everyone, I'm Chloe, this is Amanda, that's Minnie, and together we're the first Magical Bridge Playground project. So, digging into the problem that the Magical Bridge Playground group tries to address. Sensory stimulation from play, especially physical play, is really important for the cognitive development of kids, but most playgrounds currently aren't inclusive to everyone. So the people we worked with throughout this process were Jay and Olenka, and they're both here today. You guys also met them. We also worked with our users, everyone who uses the playground, kids, adults, caregivers, and parents. And being in such close touch with these people throughout the process was awesome as we began exploring solutions and breaking down ideas for our design. So the need we identified was a few-pronged idea. So first, we wanted to create a solution that does not require any transfer, so fully wheelchair accessible. Second, we wanted to create something that's stimulating for all the senses. Third, we wanted to create something that uses underutilized areas of the park, such as the areas around the perimeter and the fencing. And we also wanted to make use of pre-existing navigation patterns to preserve the flow and natural design of the park. And also, lastly, we wanted to create something really creative and exciting and very whimsical for kids to experience. So, entering this solution exploration process, we focused on a few of the existing solutions in the park that really inspired us throughout our design. So, the main two were, one, the laser arch and the sound-triggered entrance gate, which you guys also all experienced. Some of the limitations we identified with these two cool features were that they're very hearing-based, so not great for the hearing impaired. Also, we took inspiration from life-size pianos, which they have at toy stores, where you can press on a key and make a noise and then inspire to compose a sound and a song with a bunch of different sounds. So the limitation we saw of life-size pianos is that it requires pressing down on something, and it's not great for wheelchair users. Lastly, we drew inspiration from Jen Lewin, who's an artist that the playground has already worked with, who creates these amazing and inspiring light displays. So to sum it up, the two main focuses we had entering the design process were, one, creating a low mobility friendly experience, and optimizing underutilized areas of the park.
Cool. So the design that we felt did both of those things ended up being a magical bridge for the Magical Bridge Playground. So what this looks like is a device where you can trigger an outcome by applying pressure to different panels where you step or where you roll over with your wheelchair. And you can see some of the ideas we were brainstorming here were maybe a water feature or something activated with a motor. Another advantage of this design was we hoped there wouldn't be space between these panels, so users in wheelchairs or users with canes could navigate it really easily. Now, when we were thinking of what the sensors would actuate, we had a few ideas. One of our first ideas was creating a water feature that was entirely contained and maybe would be filled with colored beads or colored balls of gel that we had seen while we were exploring designs. However, given our technical backgrounds, this wasn't really feasible for the time frame we had. So ultimately, we decided to do something that would produce kind of a similar effect, which was LEDs. So here you can see the LEDs in our prototype. How this works is you apply pressure to each of the panels and they control the corresponding lights. In the real world, there would be a symmetric railing on this side as well, and symmetric lights over there, and it would of course be a lot bigger so that you can step on it. Here we have a very quick video demonstrating how a wheelchair would roll over it. It's kind of hard to see, but see if you can catch it.
Cool. I can do it again.
It's cool. Yeah.
One more time.
Cool. So the technical elements that helped make this happen was this really incredible LED strip, which each of the lights are individually addressable, which means we can control them each individually, and we can also set them to pretty much any color we want. So we set them to fit the Magical Bridge Playground color scheme, because we thought that would be a really great way to tie it into what already exists at the playground. The other really key element of our design were these force-sensitive resistors. So these are pretty simple. They change resistance as you apply pressure to them, and then you can detect that change using code. These are also actually the most expensive part of our design. You see they're about $12 a piece. So pricey, but really worth the cost for what we wanted to Finally, we used Arduino and coding in Arduino to be able to program the bridge. It's pretty simple code. It lets you program the brightness, the sensitivity of the resistors. You can see us choosing the color and lighting up the lights depending on where the user steps or rolls over with their wheelchair.
Okay. When it came time to test our design, we took the prototype to the park so kids could see it. We got 2 big thumbs up from that cute user. We actually pulled these pictures from the Instagram story when we took it there. We also saw that kids found a lot of different ways of interacting with the toy. They would either play together to come up with different patterns, or they would just go crazy and press everything, like this one right here. He was actually very excited. He told us that he would want to take it home. Then he added that because my laptop was connected to it, he had to take the laptop too. Might have been ulterior motives there. And who works with Magical Bridge also brought up an important point, which is that the fact that wheelchair users have a very unique way of interacting with the bridge, it makes them the cool kid, or it would make them like the star of something that you can play in a unique way with your wheelchair. He also seemed pretty excited about the project. For future plans, we could make a programmable bridge so kids could intentionally misprogram it. So if you step on the pink panel, the blue lights would show up, and that way they could interact in different ways. We could also provide multi-sensory simulation by including sound, which the park already does, and it would make it more of a xylophone. So if you step on a specific panel, it will create a sound. They posted on social media the pictures when we were testing it out, and someone brought up a really important point that we have to test with kids that are prone to seizures. So for that, we could change the wavelength of the light or the timing, and also adjust the brightness so that it would be less of a danger. Also, we found that the park was really busy when we went to during like peak hours, which would be around midday when it's really bright outside. So maybe to make it more fun for kids that don't want to be in big crowds, we could make it fun when it's like later in the day or when it's darker, or even make it fun for us grown kids, because I would love to go to a park that just shines at night. And that's it. Thank you.
Okay, next is Team LL Bean, LLC.
Hey everyone, so we're the former lighter leg braces team, now the modified drop block mechanism team. I'm Evan, this is Oscar, and that is Ben. We will let Ben speak for himself.
To briefly recap from our midterm presentation, our user is Dr. Peter Stansky. He wears a CAFO leg brace to support his leg because his right knee is unstable. However, he's unhappy with his current brace and is dissatisfied specifically with its weight and with the reliability of the lock system. Our initial project goal was to create a lighter leg brace, but we realized that that goal was not feasible, so we pivoted to focus instead on improving the locking system. The goal of our design is to create a modification of the existing system that automatically engages the lock with a reliable mechanism that is easy for Dr. Stansky to use. With these objectives in mind, we began our design process. We started by looking at other commercially available CAFO joints with automatic locking features to see if there were any ideas or components that we could mimic or adapt in our modification. We then came up with a few ideas of our own, including a single tension string connected with a cable, a compression string that would push the lock down over the joint, and an elastic mesh that could create a lower profile tension locking system. Our final design is a dual tension spring system. When the knee is fully extended, the springs pull the lock over the joint. When the lock is disengaged, the knee can be flexed. We opted to include 2 springs because an additional spring would prevent the lock from rotating unnecessarily as it moves. Going to Ace Hardware to purchase the springs ourselves was incredibly helpful since we were able to test them in person and find a spring with the right stiffness that provided sufficient extension and stability, but would still be easy for Dr. Stansky to disengage.
All right, thank you, Ben. After designing that drop lock mechanism, we needed to find a way by which it would interface with our user, Dr. Stansky. So that meant designing a handle. So the handle consisted of an easy-to-use grip that Dr. Stansky would use to pull and disengage the lock, and that handle would be sliding within a railway system. If this were implemented onto the brace itself, that's what the side view would look like, and the handle would be on the top thigh upright, close to the hip. And so we ended up using a purchase grip as opposed to making one that would be in this black box. And then here's a cross-sectional view of that sliding handle mechanism, which would connect to a cable and run down to that drop lock. The final design was made for our fixture that we have as opposed to the leg brace, because we don't have a leg brace available to integrate it onto. And so you can see the sliding mechanism here, and the handle is that over there, and then that's our cabling system that we ran through down to that lock. And then we also had to design a fixture since we didn't have that leg brace, which is essentially a really nice box. One of the key components here on the box was deciding whether we'd have a shaft that would run through the joint and then into the test fixture itself. However, we kept the joint self-contained and used a bolt that only ran through that component. This is the final design for that test fixture. And as you can see down here, the joint and the lock came in through the bottom, and then we attached that handle on top for demonstration purposes.
As for what this actually is, the way we manufactured it, it's mostly laser cut. Everything except the small metal lock ring was created in PRL, just from various layers of mostly 1/8 inch thick Duron for the dark parts. The rest is acrylic. Try to ignore the fact that the Duron parts look kind of like a guillotine. So those were assembled together. We left some overlap so that the joints would fit together cleanly when we super glued everything. Moreover, as for the actual assemble drop lock, we have it down here and you can play with them on Thursday, but as Oscar was talking you through, these white components represent the actual weight supporting parts of the brace. Meanwhile, the sort of transparent portions are just our test fixture, and the rest is the supporting area for the hook and the spring. So you can see Oscar's lovely hand modeling there, demonstrating a little bit of how this works, as well as a picture of the complete thing. As for what we might do in order to bring this to a truly marketable product, first would be to acquire a brace that we could actually test on. One major constraint in this project was the fact that we really don't want to take one of Dr. Stansky's 2 functional braces and start drilling holes in it, because that's a really bad idea, because he kind of needs the brace to get anywhere. Additionally, there's some features of our design that we need to test for reliability or for simple user suitability. One of those is, are the screws going to work over time? Will they fatigue? How is the cabling? Dr. Stansky likes to keep his brace under his pants, and his pants are not particularly baggy. So both the cabling and the hook must be constrained in such a way that they don't interfere with his pants, or that they don't get caught and somehow suddenly activated by that bending. Finally, Dr. Stansky, we'd love to, you can get springs with a wide variety of different spring constants. It's important to test and see that the strength we choose of spring is right for his hands and how much force he wants to apply. Then the last thing is that this is, the leg braces are usually replaced on something like a 3 to 5 year basis. We want to make sure that you wouldn't have to replace this element any more often than the entire leg brace itself. So, thank you.
Okay. Next we have Team Harnessing Power.
Eric.
I'm Kelsey.
And this is our project, Hybrid Harness. So our project, we were to modify a transradial prosthetic device. What a transradial prosthetic device is, it's a device that's used by amputees who have been amputated below their elbow on their arm. Currently, there are two things that you can use. The body-powered harness, and the one that we have here is powered by biscapular abduction, so that's when you make this motion here. The other ones are myoelectric prosthetic devices, which use sensors that detect electrical signals in your arm when you contract and expand your muscles. So here's Gary Berg. This was the person who gave us our project. And when we first started this project, we talked to Gary, who is our user. And we chose Gary as our user because he wanted us to create a device, not necessarily to be used by amputees, but for him to really get some new ideas and some new designs on how they can make these devices easier for people to use. And so the things that we came out of that conversation with were, one, to decrease the motion that amputees would need to use in order to operate the device, decrease the discomfort that amputees feel, typically in the shoulder, on the shoulder straps, keep the device lightweight, keep it durable, and keep the mechanism of feedback that they typically have when wearing a harness. For our technical requirements, we needed to make sure that whatever mechanism we use could pull 2 to 4 pounds of force with 2 inches of excursion. And so what excursion is the length of wire that needs to be pulled in order to operate the hook. And when we started researching, we really wanted to focus on the limitations of each of the devices that are already out on the market. So for the standard harness, that included, it took force to operate it. It was an obvious motion used to operate. And then also the harness can be uncomfortable, like we spoke of before. And for the myoelectric device, there was sometimes a delay when using the sensors. The sensors didn't necessarily always work. It was expensive, and it was minimal to no haptic feedback for the user.
So this is a schematic of our chosen design. You can see that we maintain the body-powered harness. And this is connected to a pressure sensor that we have, which is then connected to a linear actuator through an Arduino. And this linear actuator, this motor, is connected to the cable which is used to operate the terminal device of hook. So these are some images of our final prototype. We can see we've got a lot of the circuitry in the back along with our linear actuator right here, and then it's still connected to the terminal device in the front. Now this is a prosthetic that Gary gave to us. He loaned it to us, and as it came, the cable that's used to control the hook, it's a little too long when connected to our linear actuator to use as it should function, and we didn't want to cut the cable because this is Gary's prosthetic. So as it currently is, we don't have our linear actuator connected to this specific cable, but for future iterations, this is something we hope to revise to be able to adapt the dimensions of this cable in order to fit the functionality. So I'll go through a little flow chart on how this actually works. So first we've got a pressure sensor, and that's located on the harness. So the user would apply a specific amount of pressure to that sensor to control how open or closed they want the terminal devices. And this pressure sensor changes its resistance based on the applied force. So this resistance is read then by the Arduino, and it correlates that specific resistance to a position that the linear actuator needs to move in order to control the hook. And then, so it both does that through the code, it reads the resistance and also actuates the motor in order to control the device. And then the linear actuator is the motor that does that. So when we got our components, we first performed some preliminary tests. First, we wanted to see for the linear actuator what speeds it operates at, also what types of forces it's able to pull. For our pressure sensors, we wanted to see what amount of pressure correlates to what resistance. And then finally for our Arduino, we needed to determine what the resistance it was reading as well as the positions that it was able to output. And we did all these this testing before to get a baseline idea of how these components would function in our overall design.
So from our looking at performance, we found that our advantages were still that it did reduce strain. We can use a lower amount of force to properly actuate the pressure sensor than would be needed for the standard harness. And also that force range is customizable per patient. So if someone needs to be carrying less or has more of a discomfort issue, then we can alter it for that. The limitations of our system currently are that the motion is neither as precise or as quick as on a standard body-powered harness. The aesthetic is not improved, and we're going to require a battery pack. Right. So our primary challenges come in this from our circuitry. First, we needed to add in a thing to switch polarity so that our linear actuator could both extend and retract. And then also we had to do significant debugging of the physical system and of the Arduino code. To calibrate the pressure sensor is a bit of a challenge because it is at some points hard to determine whether the force being applied is intentional, so that's something we're going to have to keep working on. And we need different voltages to operate the Arduino and the linear actuator, so that's another. Alright, looking at the future, first we'd like to optimize our materials. With the batteries, we'd like smaller and more portable batteries, a faster motor that's more responsive, and we would like to collapse our circuit into one integrated circuit. We'd also like to look at other more precise sensors. Then beginning user testing with some of Gary's actual patients, and then iterating our software based on that and how we are controlling based on the applied forces. And we'd like to simplify the harness design a little more and do the reintegration of that cable. All right. Thank you.
Okay, next are the 3 cookies.
Hey everyone, my name is Alex.
I'm Amy.
And I'm Rachel.
And together we are the 3 cookies. So today we will be presenting our project called Moving Forward, which is all about creating a hand-powered playground ride that is inclusive of people who use wheelchairs. This quarter we were also working with the Magical Bridge Foundation, which focuses on building a playground that is inclusive of kids and adults of all abilities. And the problem that they address is this need for accessible playground structures. And not only making them accessible, but also making them active and fun. As we heard, there's been extensive research done that play is an important part of child development. It can improve their cognitive, social, physical, and even emotional well-being. We've also learned in this class that 1 in every 5 people has a disability, so the magnitude of this problem cannot be overstated. Our project specifically was focusing on the 2.2 million wheelchair users in the United States. Now, there's been a great amount of work done to this day. Data shows that there are over 2,000 accessible playgrounds. But what does it really mean to be accessible? As you can see in this accessible playground, there's this wide ramp and a shallow slope that allows someone in a wheelchair to access a lot of the playground structures. But at the bottom, you can see wood chips, which, as we know, is a big problem for wheelchairs, and it makes it really difficult for them to maneuver. So we see that there's still this disconnect between being ADA compliant and being actually accessible and welcoming for people with disabilities. To get a better grasp of the issue we had, we actually interviewed my cousin. This is Roger. He was born completely deaf, so he has a lot of experience maneuvering through playgrounds with a disability. And our favorite quote from that interview says, "I remember going to playgrounds as a kid and having an absolute blast. I think that people assumed because I was deaf, I didn't have an imagination. Give any kid something simple and cool, and you can bet they will find a way to make it fun." So, coming out of this, we were inspired and energized to enter our ideation phase, which Amy will talk about.
So with Roger in mind, we decided to dream big during the brainstorming process, coming up with ideas even as crazy as a wheelchair zipline.
I'm going to be talking and pitching our 30 plus ideas to Jay Gluckman, who works at the Magical Bridge, and he gave us really great feedback. Some of our biggest takeaways from these conversations were understanding what an accessible structure looks like. Understanding that one structure may not accommodate every single person's needs, so it's good to have a target population, and also that people who are active in wheelchairs can increase their longevity, and that is something that we ended up targeting. But before we got there, we had to narrow down all of our different ideas. We had the interactive kitchen, which was making the kitchen at the Magical Bridge a little bit more hands-on, adding movable structures, but we ended up not doing this idea because we weren't as excited about it as our other ideas. We had a one-at-a-time slide, which focused on making users use a slide one at a time, and so we ended up vetoing this idea because there's already so many slides at the Magical Bridge, and we were worried about the user acceptance, and we were worried for safety. We also had, and then we decided upon our hand-powered ride, which would use a hand motion mechanism in order to move a ride forward. And so we ended up evaluating it for these criteria. We felt that we could do it within our estimated cost of $200 that Dave is providing us with. We felt that users would accept it because it was fun and it was exciting and it was also safe. And during this whole process, we enjoyed the challenge of figuring out what technical and engineering skills we would need in order to make this happen. And so the specific need that we addressed was creating an active wheelchair accessible structure. Although there are already solutions to this, the problem is that they are costly. For an individual to purchase one of these types of items, it would cost thousands of dollars. And so what the Magical Bridge addresses is this issue, is making a public space inclusive for people to play. And Rachel will talk to you through our many iterations of creating this design.
Yeah, thank you. So, keeping all of this in mind, we went to the PRL. After talking to the PRL TAs and also seeing what low-resolution materials we had available to us, we ran through a couple more iterations of our final idea. We thought about doing a seesaw structure, a rotating disc platform, or even incorporating a tricycle design into our prototype. Through this process, we decided on 3 main priorities that we wanted to incorporate into our project, and those included an accessible seat, a hand-powered motion, and an individualized experience. We ended up really liking the roundabout merry-go-round idea, and as you saw in our midterm presentation, we created a low-resolution prototype incorporating these 3 priorities. However, there were some problems with this prototype. Firstly, the rubber bands that connected the wheels slipped a lot, creating unpredictability. The chairs were also not ergonomically set in a way that made for comfortable hand pedaling motions. And finally, the structure overall was fairly unstable. In order to address these issues, in our second prototype, we turned to Legos. We also aimed to optimize the individual buggy of the merry-go-round system. We used a Lego chain, which solved the slipping problem and increased the stability and the predictability of the movement of our prototype. We were also able to 3D print a chair using a model and fit it to our buggy and the mechanism shown. Our final prototype ended up turning out very well, and we want to show you a video of the mechanism of movement that we ended up using. So here's a little guy in our chair. I'm not pushing it at all. The only motion in this video is coming from the hand-powered crank motion. In our final project, which we are looking forward to showing on Thursday, the seat will be connected to a midpoint, which will be rotating around. So, looking forward, we also want to scale up our model. We want to add more seats. We're thinking 4 or 5. We want to change our materials to more sturdy things like metal and different plastics, and increase the safety of our prototype by decreasing the pinch points. And eventually, we want to get our prototype on the market. Based on our research of other playground equipment, the estimated cost for this would be about $5,000 to $10,000. And yeah, thank you very much, and look forward to seeing a hand-powered merry-go-round at the next Magical Bridge you visit.
Okay. Last but not least, we have Uno Dos Tres.
you've been signed out, sign into your account for another 10.
Sorry about that. I don't. Okay, we're gonna try something different. Okay, go.
I'm Heidi, this is Jacob, and we are the Uno Dos Tres, and we are working with Fernanda on a workstation for her wheelchair. So the workplaces and coffee shops and public areas in the Bay Area where you want to go and do outside work are very crowded and often not very wheelchair friendly with limited wheelchair accessibility workstations. So Fernanda suggested that we make her a laptop workstation where she could essentially use her wheelchair as a accessible place to do work outside of her home office. The need is a portable, non-slip, lightweight, easily access, portable workstation where she can keep it in her purse, pull it out when she needs it, work on her laptop, do any type of writing that she might want to do. The current laptop desks that are out there are much like this one. They're not portable, they don't fold, they're very heavy and very expensive. Here's another example of a laptop desk. This one is obviously one you could not bring anywhere. It's pretty, but it's also very expensive, close to $200. So we looked elsewhere for foldable, portable items, such as this stool, which has a folding mechanism that we wanted to mimic in our prototype.
Yeah, so in prototyping, we headed to the PRL, and we decided to work with wood. It's really easy to use. It's pretty lightweight. Yeah. So as you can see, this was one of our main prototypes. Went to Home Depot, bought some wood and hinges. So this is it, freestanding, and I'll fold it up on the left. You can see that it fits in your hand pretty easily. For our final model, we would ideally use thinner material, probably plastic, because that'd be lighter weight. And one of the problems we were having with this was that the hinges don't stop at 90. They actually go past, which is something that we needed to fix for our final design. Akash couldn't be here. He's in Germany right now for a gymnastics meet, so this is his part.
We brought this first prototype to Fernanda to see what she thought of it, and we were able to glean some very valuable information. First, the tray was too wide. When fully open, the legs of the tray were farther apart than the width of Fernanda's wheelchair, so we knew we had to make the whole thing a little bit less wide. Fernanda did note that the height of the tray in this prototype was perfect, so we were sure to keep that in mind for our next iteration. We tested this prototype on ourselves, but we didn't realize that Fernanda sits much farther forwards in her wheelchair than any of us sit in a chair. Because of this, when she was using it, the front legs of our prototype were just hanging off the end of the chair, not actually standing on anything, so the tray kept tipping over forwards. The hinging legs that we created were also unrestricted, so they would hinge well past the 90 degrees we wanted them to stop at. With these comments in hand, we started towards a better tray. Our updated design began folded up in half, just like the previous design. Since the back legs were not a problem in our last design, we chopped the leg design from our last prototype in half and kept the back half. For the front legs, instead of opening out to the side, we decided to have them open out to the front. These legs are much wider and are circularly carved out on the bottom to fit comfortably on top of the legs of the user.
Yeah, so after we met with Fernanda and then catted it all up, went back to the PRL and made final one, which, as you can see, has the rounded, wide wood pieces that your legs fit in flushly, and then these back legs still sit on the chair. Since it was too wide, the first prototype, we did have to narrow it a couple inches, which wasn't very hard to do. And then, not in these images, but for the final product we have for Thursday, we added stoppers for each of the legs to stop them from flying all the way out and falling over. Yeah, so for future fixes, like I said, wood is great for prototyping and using in this case, but ideally we would use injection molded pieces. It would be a lot cheaper, you could make lots of them, and it would be the exact same every time. And that would also fix our hinge problem that we were having. And like I said, it's very cheap to mass produce lots and lots of plastic pieces, and it'd be lightweight. And for our final project, we did have a silicone baking sheet to put on to make it non-slip for the laptop, and we could use molded plastic surfaces to accommodate that purpose. Thank you.
Thank you.
Okay, well, I want to thank all the teams for their excellent job and their efforts throughout the quarter. Let's give them another hand. Please leave your evaluation forms on your desk. Somebody will pick them up, and you're welcome to talk to the individual teams. And if you need to go, I'll see everybody on Thursday with burritos in my hand.